Okay, a very good afternoon to everyone present here. My name is Saurabh. I'm from Stellar Universe. So today's talk will be by Nidhi Saini. She's a PhD research scholar from Department of Physics and Astrophysics, University of Delhi. She'll be talking on fast radio bursts and their mysteries. If you guys have any questions, we'll be having 15 minutes session at the end of the talk. So you could just drop your questions in the chat box itself. Uh, yeah, so over to you, Nidhi. You can continue.
Yeah. Hi everyone. So I'm gonna talk about fast radio burst, and if you guys have any questions, so just ask me in between. I would rather try to make you understand about these astrophysical phenomena, and let's see if we can, finish the talk within the time limit or not. Okay, so let me first start, and please let me know if everyone is able to hear me or not. Let me know because okay, I'll just go ahead. So let's talk about first the radio sky. Uh, what is radio sky? You might all be very well aware of electromagnetic spectrum, and radio waves, as you can see, share a larger part of the spectrum, right? So, radio is very important to us. Why is that so? Because the radio frequency or the wavelength from any source in the universe reaches directly from the source to us without any obstacle, because the atmosphere of Earth is sort of transparent to the radio waves. So you can see from this figure every wavelength has certain windows. For example, visible, if you can see, you can directly have a telescope on Earth's surface to observe the visible light from any source. And similarly, for the radio waves, there is a huge window which is available for the radio wavelength, right? Now, let's talk about radio astronomy, why it is so important. And of course, you can see that radio astronomy is very important because most of the sources, like you can say black holes, if you have heard of neutron stars or pulsars, better to say, or many radio sources are available in the universe, and we just need to pinpoint in that location if we know, or anyhow we can detect them from the radio telescopes all over the earth, right? So just let me know in between because I cannot hear you guys. Now let's talk about few terminology that we used in radio astronomy. Uh, Few of them are known to you maybe, and let's see. First of all is luminosity. Luminosity is nothing but the total amount of energy emitted per unit time by any object, right? And the radio flux can be defined as the luminosity per unit surface area. Then there comes flux density. Flux density is the flux received over a band of any wavelength. Any wavelength, that will be called flux density. And if we talk about radio flux density, it will be radio flux received over a given certain bandwidth divided by that bandwidth. That will be called radio flux density. But when we talk about radio, we generally prefer fluence, which is nothing but flux multiplied by the pulse duration of that source that we have detected from the telescope. Then there comes surface brightness. Average apparent brightness. Please be sure that it is apparent, not the absolute. Apparent is what we are seeing, what we are observing. That apparent brightness from the source per unit surface area of its image, that will be called surface brightness. It is very important because when we talk about surface brightness, uh, it is a certain quantity which do not change over a for given type of sources. That is why it is very important. Then there comes brightness temperature, which basically tells the temperature of the body, of the given body, of any body. Uh, if if any black body would have emit the same kind of brightness. For example, if I have any source, I compare its brightness with a black body, which is, black body, you guys know that it emits all the wavelength to its surrounding. So that temperature of the black body would have the same amount of brightness as that of given source that we are observing. Then the most important quantity that we are gonna deal here is dispersion measure. Dispersion measure, if you can see in the figure, there is a source, and we are observing here on Earth. There will be some gases, some let's say dust particles, or better to say plasma is in between from the source to the Earth. That plasma would have free electrons in it, which is represented by Ne. Ne is, if I just plot a cylinder from the source to the Earth, the number of free electrons in that cylindrical column multiplied by the, or better to say, integrated over the length or the line of sight will give me the quantity called dispersion measure. So dispersion measure sort of indirectly tells me that how much, if let's say if the any or the number of electrons are for called plasma, generally we take that the gaseous component or the dust particle in the universe is the density is not that high, right? Then most of the component from in the dispersion measure is coming from the length or the integrated part of the length. That means it basically tells me the distance of the source from the earth, right? Okay, let's move ahead. You guys might have heard about various violent events in the universe. Uh, if any one of you can tell me what kind of sources can be categorized into violent events, you can unmute your mouse. I don't know whether you can unmute your mic or not.
Yeah.
Oh, okay. So basically, you might have heard of supernova. Supernova is a phenomena when a star, or better to say, a white dwarf, extends its mass limit, which is 1.4 solar mass. Then it undergoes into a blast. That is called supernova. And then there comes gamma ray burst. Gamma ray burst, as the name suggests, it is a burst only observed in gamma rays for few seconds or minutes. They are categorized into different categories depending upon the time duration of their detection pulse from the telescopes. Then now is the most mysterious astrophysical phenomena comes as fast radio burst. These all are artistic pictures depicted what they could, how they might look like. And fast radio burst is something that we don't know anything about. Or you may find out at the end of the talk that we may know something about it now. So let's talk about fast radio burst. First of all, what are they? The first fast radio bursts have been observed or has been found, better to say, because it has been found in an archival data survey in 2007 by Duncan Lorimer. We'll talk about it. So, just a decade ago, they have been observed. The most mysterious thing about fast radio was that they are only detected in radio. There is no electromagnetic counterpart for the fast radio burst. We do not know whether the sources that are responsible for fast radio burst can emit in other wavelengths also. People are trying to do various other things. They are trying to, they are trying to associate like they might emit in other wavelengths also, depending upon certain scenarios. The typical pulse duration is millisecond, few milliseconds only, and they are high intensity or high luminosity objects. The typical luminosity is 10 to power 43 to 10 to power 45 per second. The peak flux density is around, it is a range that is given in the FRB catalog. Um, it is available online. You can check it out for a given frequency range. That means all the FRBs are detected within this frequency range with these flux densities. And the flux density unit is Jansky, which is 10 to power minus 26 watt per meter square per hertz. So it has been named after Carl Jansky, which sort of initiated the whole astronomy, radio astronomy thing. Then we have already talked about the dispersion measure. This dispersion measure is telling us about the distance of the source. So mostly people believe that they are not from our galaxy; they are extragalactic objects, or some of them are also suggest that they are sort of cosmological objects. Why it is so? Because people have mapped all the values of dispersion measure within our Milky Way. For a given line of sight, we know the value of, or the highest value of dispersion measure for a given line of sight, right? So this value is way too beyond, way too large, way too high than the expected dispersion measure value for our galaxy for a given line of sight, right? So that is why we assume, we believe that they are not from our galaxy. Then we have talked about brightness temperature. Brightness temperature one can easily find out by this expression. The typical brightness temperature is 10 to power 35 Kelvin, which is sort of an indication of kind of emission process in the at the source. What kind of emission is happening at the source that is giving rise to such a high brightness temperature? Remember, please do note that it is not the normal temperature, it is not the thermal temperature that we generally talk about, it is brightness temperature, right? Now, how do we name them? It is named after following FRB, then the year, YYMMD. So if we just talk about FRB 010724, that means 24th July 2001. The first FRB, named Lorimer FRB, why it is named so, we'll talk about it, has been detected in 2001. There is an interesting story behind first FRB, which is basically discovered in 2007 by Duncan Lorimer and his that time PhD student DJ Narkovic. But if you see, the nomenclature suggests that it has happened in 2001. So after 6 years gap, a PhD student put up an archival data and find out that there is something unusual behind this particular pulse, radio pulse, which is that the time duration of the radio pulse is 5 millisecond, DM is 375 per cubic centimeter per second, which is much higher than the corresponding galactic contribution as we have talked about earlier. The peak flux density, galactic latitude, all of these certain parameters are suggesting that this is not something that we know of. This is something new. That is why Duncan Lorimer pursued this, and up to 5 years, there was no any kind of detection or any kind of discovery, any kind of found out of such pulses, such radio pulses. So up to 5 years, it was sort of vague idea that they are something new. So, but Lorimer, of course, persuaded it, and finally, it is now a very big astronomical phenomena that people globally talk about. Now we have 126 FRBs from 10 telescopes in real-time detections as well as archival data surveys, right? Now we have interferometers, better sensitivity of telescopes. That is why we have certain confidence that in the coming days the number will be higher, way too high. So let's talk about this dispersion measure, which is basically how do we talk about this dispersion measure? How do we say that this dispersion measure is interesting quantity? So let's say that from a source, wave band. Wave band means, let's say, a wave band from mu one to mu two, slightly different. Mu one plus, let's say, d mu is emitted from a certain source, and we are observing here it on Earth. What happens that the higher frequency in this cold plasma reaches us faster than the lower frequency. So this generates a time delay between the higher frequencies to the lower frequencies. Of course, the higher frequencies are reaching us faster. So what we do is we observe the arrival time, which is on the x-axis of this figure, with the frequency. So let's say mu one is the higher frequency, mu two is the lower frequency, and in between there are other frequencies. So higher frequencies reaches us faster than the lower ones. So this generates a time delay, which is associated with this expression with dispersion ratio. So any dl integrated over 0 to L, 0 is our position, L is the length or length of the cylindrical column that we have talked about, basically the distance of the source. So this is called dispersion measure. So this arrival time delay is directly proportional to dispersion measure. So we have a uh, direct indication of let's say the distance of the source. Now, of course, this signal is traveling from the source, from the intergalactic medium, uh, from our Milky Way galaxy, and then reaching us. So, this dispersion measure will contain all kind of components within the total dispersion measure. So, this is how dispersion measure works. Now, let's talk about we have detected 126 FRBs. So, how do you signify that all of them are same? We don't know. In fact, we know. We know that certain FRBs are different from other FRBs. So we have 126 out of 126. We have uh, 10 or 12 FRBs such that they are named as repeaters and others as non-repeaters. So non-repeater FRB are something with a radio flip and it just goes off. You'll never find it again. You don't know from where it is coming from, anything about this non-repeater FRB, non-repeating FRB. But for repeaters, we know because if we have sort of radio map in the sky of the repeating FRB, then we'll just follow up that particular repeating FRB from other telescopes. But we just wait because it is not reading. We don't know when the next pulse from the same source is coming to us. It is just repeater because many pulses are coming from the same location, from the same source, from the same distance. We do that because we know dispersion measure, because we know the sky location in the radio map of the sky, right? So depending upon these kind of two categories of FRBs, as we have talked about until now, we don't know what kind of sources, what kind of progenitor models can generate such kind of events, which are highly intense but happened only for milliseconds. So within millisecond, they just emit a huge amount of energy, but they are not from nearby sources. They are from extragalactic sources due to their high dispersion region. So let's talk about their mysteries. Their mysteries include the progenitor models, which are mainly categorized between non-cataclysmic and cataclysmic, depending upon whether they are repeaters or non-repeaters, right? So non-cataclysmic are those. are the models that are responsible for non-repeating FRBs or repeating FRBs. They can do both kind of things. But cataclysmic are the ones that are responsible only for non-repeating FRBs, right? Cataclysmic event means that some event happened and the source which is producing that event has been destroyed in the process. While in non-cataclysmic, there will be certain remaining part of the initial source will be there. There will be some remaining part, right? For example, if we just talk about non-cataclysmic models, they can include giant pulses from young neutron stars, collision between asteroid and neutron stars. I hope you guys have heard of neutron stars. So what happens when a star, the core of the star, what happens in the core of star, that there is a due to gravitational pressure, huge pressure inside the core, the electrons and protons and the neutrons lose their identity and they just crushed further and they form there will be higher density of neutrons and those particles, those nucleons, better to say, are held by the neutron degeneracy pressure inside the core of the neutron star. So that's particularly kind of behavior is categorized as the neutron star. Then there comes different other models. We'll talk about them briefly. And in the cataclysmic models may include collapsing compact objects. For example, if I have a neutron star, black hole, white dwarf, any kind of compact object, it is collapsing individually. For example, we know what would happen if a neutron star collapses into a black hole. What would happen, right? Then there are certain other theories also, like mini black holes, quark nova, quasars. We'll talk about certain of them, but one thing to add here that the progenitor models proposed for FRBs are way too it's like each and everything which can explain such phenomena in radio wavelength that are sort of modeled as source of or the progenitor models of the FRBs. So let's talk about the first doubtful signal, what it can be. So how all this scenario started. So it was a new phenomenon that time. Let's go back 10 years back, and FRB was sort of into as considered as new thing, right? Then there comes certain Parkes telescope in Australia picked up a certain signal, but that signal was equally spaced pulses with equal brightness, and it was not seen in any other telescope. It was named as barytons, and the number of signal, the peak rises at the midday. So what was the real culprit behind that is the microwave oven in that cafeteria. What happened? They have conducted a very good scientific experiment. They opened the door of the microwave just before when the food was, cooked, perfectly cooked or hot. So what happens that the microwaves escape from the oven, renders into the atmosphere, and reflected back into the telescope as a signal. So people early days try to associate the two barytons with the FRB, but after this conducting of scientific experiment, we know that barytons are not the FRBs; they are something different. So, as the model suggested, that there are compact object mergers. Let's talk about binary neutron stars. What happens when a binary neutron star? Of course, they will have magnetic field, and their magnetic field is around 10 to power 8 to 10 to power 10, or may go to 10 to power 11 also. Boss. What happens when two differentially rotating neutron stars merge together? to form a hypermassive neutron star, what would happen to the magnetosphere of the magnetic field lines, and it is picked up as a FRB signal. So this happens when there is binary neutron star merger, but there are other compact object interaction also. For example, neutron star white dwarf can also generate FRB, white dwarf, black hole white dwarf. So certain various combinations are available as progenitor models in the FRB field, right? Then there comes non-cataclysmic events, and this magnetar model is very popular right now because we'll talk about it in the coming slides. Magnetar is nothing but a neutron star having magnetic field greater than that of surface magnetic field that here we are talking about. It is 10 to the power 14 cos or more than that. So what happens? Young magnetars. Of course, whenever we talk about radio and pulsars, it is always associated with the magnetosphere. So what happens that charged particles accelerated through the magnetic line of field in the magnetosphere of the magnetar, and they produce via synchrotron radiation, or better to say curvature radiation here, they produce radio burst, and that is depicted as fast radio burst. And this is most popular model right now. We'll talk about it in the coming slides. Then, for example, let me talk about strange star. What is a strange star? Just like the neutron star. Uh, when let's talk about from the starting. White dwarf. How does white dwarf come into picture? When the core inside the star, inside any star, when the force inside the core exceeds uh, the a certain limit, let's say certain limit, and all the electrons just lose their identity, and the gravitational pull is held by the electron degeneration. Same has happened in the neutron star, but in the neutron star, neutron degeneracy pressure is responsible to hold back the gravitational force, just so that the star will not collapse. In the strange stars, it's a right now it's a hypothetical thing because we do not observe it, but theoretically it is possible. Just like in those scenarios, if the gravitational pull exceeds certain limit, what would happen that the neutrons and protons lose their identity, and they just form a quark gluon plasma at the core of the star. But outside there will be electron layer at the surface of the star. That is known as a strange star, and of course the crust is made up of charged particle material. So what will it do? It will accrete matter from the surrounding, and because of this accretion, it will collapse and emit a large amount of energy, which is stored in the magnetic field. And what would happen then? The charged particle from the polar cap region will emit out, and they will generate a radio burst. The relativistic charged particles along the magnetic field lines, they will emit radio burst, which is known as which is known as fast radio burst. But there is a caveat, or not caveat, there is a possibility of X-rays and gamma rays emission from such models. So this is happening within the crust of the strange star, but there is something called star quake also. Just like earthquake, stars can also have quakes, and people have studied the aftermath of the two, and they found striking similarities between the uh, Richter scale of earthquake with the energy distribution of the after quake of the star, and they found that they are quite similar. So one can depict that the star quake can also be responsible for the fast radio burst. Just remember one thing here: they are non-cataclysmic, so they are responsible for these all models are responsible for repeating FRBs. They can explain the repeating scenarios of FRBs. Then there comes collision between neutron star and comets. For example, a neutron star is sort of going through a huge comet environment or asteroid environment. So what would happen? The material from the comet will get attracted from the gravity of the neutron star, and the charged particle will get separated, and they will travel from via magnetic field lines and produce fast radio burst. Of course, there are certain mathematics which find similarities between such things, such models with the FRB. That is why they are suitable model for FRBs. Now, let's talk about aliens, because aliens are everywhere. So, what happened just few days back, a few years back, I think in 2012 or no, 2016, maybe 2016, a Harvard researcher put out a theory that FRBs are nothing but they are propulsion engine emission from the alien spaceship. So, alien spaceship is sailing through the space, and the Earth is positioned at an angle that we are getting the FRB signal from the propulsion engine, right? Sort of like we know about how rocket works. So, but it's aliens. So let's forget about it. It is just for fun. Then there are other models. If you guys are interested, you can go through them. Let's talk about how to resolve the mystery. If anyone can guess, the mystery can be resolved by the eyes of the Earth. And what are the eyes of the Earth? Because we cannot observe in radio. There are certain instrumentation called radio telescope. They can observe radio, radio burst or radio emission from any source. So these are just few telescopes. First one is Parkes. Parkes was the first telescope which has detected the first. The Lorimer Burst was basically from the archival data of Parkes. And in the initial days of FRB research, Parkes was the only dominating telescope among others. Then there comes Chime. Chime is very important right now. What is basically Chime? Chime is Canadian hydrogen intensity map of experiment, right? So it is conducting experiments in hydrogen line, and FRBs are also detected in certain radios, those particular given wavelength. And most of the FRBs right now, or better to say, we are expecting huge number of FRBs from China, and it has done that. China has proven that it can do that. It can detect many number of FRBs within a day in the future. Then there comes the third one is Arecibo. I hope you guys might be aware of it, and if you are not, you can go through their particular site and find out about their interesting facts. Let me just talk about one uh, escape, utmost, and GPT. GPT is Green Bank Telescope. Escape is SKA basically, SKA survey, and utmost is basically uh, uh, it is a collaboration between Swinburne University with the Sydney University, and it is right now very have to be is utmost is proven very good for the FRBs right now. So how many FRBs are detected from given telescope. So you can see that 35 are from ASCAP, Parkes 30, Chime is detecting many, and all the repeating FRBs except one, which is the first repeating FRB. Except that FRB, all the repeating FRBs are detected from Chime. So that is why Chime is very important for us, right? And they are detecting in different frequency, their location, so you can find out from their particular websites. So the point is, did we really resolve the mystery? Did we? There is a recent news that I'm gonna share with you, that a magnetar has been pinpointed for the repeating FRB. This repeating FRB, 180916. This is a very recent news, and an immediate follow-up by VLBI network detected 4 more bursts from the same source. And it has been located into a spiral galaxy named SDSS, this particular FRB, this particular galaxy. So it's sort of narrowed down the progenitor model of the FRBs, which suggests that magneta can be proven a good model for FRBs. Of course, let me talk about the first FRB. It was also located into a dwarf galaxy, and uh, people have done a lot of work on this particular FRB. They have detected that the source of FRB 121102 is lying into a extreme magnetic environment of the dwarf galaxy. So it's like when we talk about dwarf galaxy, we talk about I mean how many number of new stars are being born inside that galaxy. That's how we talk about the dwarf galaxy. So it is expected that a magnetic environment is possible for that source. So why repeaters are important? Because they give us more information. That is why we should look for repeaters instead of non-repeaters. In fact, people suggest that every FRB is a repeater FRB, but we just only pick up those signals which are high enough for us to detect. So, for example, if I take any non-repeating FRB, people suggest that that particular pulse from that repeating FRB, it is not non-repeating, it is in fact repeating FRB, but the pulse that we have picked up is the highest intensity pulse that we are able to detect from that repeating FRB. So this theory, I don't know whether my personal thing is, I don't know whether it is possible or not. I mean, it is possible, but theoretically, if we just count the numbers, only 10 or 12 are repeating FRBs among 126. Why cannot we detect others into the same manner? So let's hope for the best. And we are a better future for FRBs because many of FRBs, see, I have started only with 16 FRBs few years back, I think 2017 or something, only 16 FRBs, and now we have 126 because there are dedicated surveys. The sensitivity is high, of the telescope is higher, and we are detecting more, and we will detect more. We know that. So let's talk about summary. We know FRBs are really second radio pulses of high intensity. Found in first FRB was found in archival data, and then there are real-time analysis also. Interferometer, radio interferometers are also there that they are detecting FRBs, and many kind of progenitor models have been proposed that we have talked about. Seem to like that the magnetar model is better model or narrowed down to be the expected future for the FRBs. Then there are dedicated surveys that are gonna give us more detections per day for FRBs. Then the multi-wavelength survey, which is very important, which is the future of every kind of astronomy. If we talk about gravitational astronomy, of course, we can talk about gravitational waves here also because of compact objects that are responsible for FRBs. So I have worked with gravitational waves also. So they the expected amplitude of gravitational waves from such compact objects are way too higher than expected from others. So I don't remember the number exactly right now, but the luminosity, gravitational wave luminosity is, I think, 10 to power 56 arc per second in gravitational waves also only. Right? So multi-wavelength or multi-messenger astronomy is the future of everything. This is the final one-line conclusion of every talk, I think, nowadays. So this was my talk I had prepared till now. So if you guys have any question, you can ask.
Um, Thank you so much. Can you see your um, desktop if you're able to
Yeah.
view the question? Just
Uh, See, I do not have any. Oh, I have questions. Okay, where are they? How does one? So dispersion measure. I have talked about the question from Surendra Padmavat is that how does one measure dispersion measure? How reliable it is to associate dispersion measure with the sense of distance? That's what I have talked about. Let me just go to the slide. This slide. If I think this slide just clears up the dispersion measure with the arrival time pulses. So if I have a radio wave band coming from a source to us, the arrival pulse for different frequency will be different, and that time delay is directly proportional to dispersion measure. So it is quite reliable for distance because the NE, which is number density of electrons, is I don't know what is the value for intergalactic medium, but it is very low, and we can expect the most of the part is coming from length or the distance of the source. Then the next question is other ways of measuring dispersion measure. So the thing is, dispersion measure, we have a better understanding of dispersion measure via pulsars. We know pulsars are everywhere in the galactic plane, right? So I have talked about electron density map inside the galactic plane, which is done by survey of pulsars, and what they have done is we know which line of for which line of sight which pulsar is there, and we know because it's pulsar, so we know how, because it is within galactic plane, within galaxy, so we know the distance. We just fit some models, and we sort of have a complete intensity electron intensity map for the galactic plane. I should not say complete, but we have a good understanding of that. Then there is a question by Ankit Kun. It is a heavier star will become so highly compressed that each proton combines to form neutron and neutrino. Okay, so I don't know whether it is a question or just comment. Then there is question by Priyamvada. What is the frequency range of detected FRB? Is it possible to detect FRB beyond that range? It should be possible. I have talked about the frequency range in the first slide. The frequency range for the given FRBs 6,000. In fact, now it is old data. Now we have 400 megahertz to 2 gigahertz, and people are trying to find out FRBs for the lower frequency range. Let me just point out one more thing here. Hoshino telescope that I have talked about in the telescope table. Yeah, this Hoshino FRB. This FRB has detected 11 FRBs at 111 megahertz. But there is issue with that thing. It is not issue, but the point is the pulse width is not so good. It is around 3,000 milliseconds to 5,000 milliseconds. So we don't know because it is not how to say it, the sensitivity or resolving power. Yeah, resolving power of Kushina is not good among these telescopes. Okay, then there is Surendra. How many are non-repeating and how many are repeating? I have told you that 10 to 12 are repeating. I think 10 are repeating the exact number. 9 out of 10 repeating FRBs are from China. One is from Arecibo, and others remaining 116 are not repeating. Any constraint on event rate? Yes, 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 yes. Event rate, there are many constraints. The typical event rate, I don't know whether I have written it or not. It is around 10 to power 4 to 10 to power 5 uh, FRBs per sky per day. So we have better constraint, but this is, I remember from the last time. Yeah. Okay, then Surendra again. Yeah, I have heard similar things, and non-repeating might be repeating too, but you gave personal opinion. Can you talk a little bit about it? Okay. See, now, I mean, this theory might have worked with the previous, or let's say 4 years back, but today we have dedicated surveys, we have telescopes that are just dedicatedly working for FRBs. So, and they're sensitive enough too. So, if this theory would be true, we would have more number of repeating FRBs. Yeah, that is my personal opinion. Okay, I hope I am answering. I'm okay. Then there is Karnika. Why are FRBs detected only in radio wavelength? That makes them FRBs. Fast radio burst. Fast, that means millisecond. The time duration is way too low. They are fast. Radio, they are only detected in radio burst. So we don't know actually. That is why there are various models. We are trying to hope that there might be other emissions. For example, I have talked about this magnetar in the last slide. Yeah, this particular magnetar. Okay, I have not written it, but there is the follow-up survey has detected X-ray emission from the same source. But yeah, there are always uh, disputes regarding these multi-messenger, multi-wavelength observation of the FRBs. In earlier, there was one FRB, one repeating FRB. I think 18 something. I don't remember the name, but that was also associated with some GRB. But then other people claim that it is not associated with that GRB due to some other reason. And then people settle down that these two were, I mean, the GRB detected and the FRB detected are not from the same source. They are separated by timeline. So yeah, okay. Then there is Surendra. What do you think people who do computational astrophysics simulation or binary neutron star? Uh, right now, they should focus on gravitational waves, I guess, because that is better than, I don't know. I mean, it is in trend. It is in trend. Yeah. See, the point is, binary neutron star mergers are very interesting, and simulations of binary neutron star mergers can lead us towards many new insights of the progenitor, many new insights into astronomy, into gravitational waves astronomy, any kind of astronomy. So you can generate templates, you can associate them with some gravitational wave detected, or you can generate templates for future. For FRB, well, there is right now simulations have not started as such model dependent basis because we have not so his question is particularly about, let me repeat his question. What should people do who work in computational astrophysics simulation of binary neutron star merger should focus on in terms of FRPs? Uh, so that is my answer that we don't know because we have not narrowed down any model right now. But if you can generate such a template which can, which can narrow down the models, which can narrow down FRV models via, let's say, GW templates or other kind of templates, that will be good. Yeah. So if you can generate the radio emission or somehow find out what kind of radio emission generate will be generated from binary neutron star merger, that yeah, that might lead towards something new, something feasible, something interesting. That might narrow down the progenitor models for FLs. I think I have answered most of the questions or all of the questions.
So if there are any more questions, you can put it in the comment box.
So Surendra is saying that okay, no issues. I understand you are trying to do binary neutron star merger in context of FRPs, how to do simulation regarding that. But honestly speaking, I also don't know because people have not started working out with the particular given model and simulate that model to generate FRP. So if you can do that, that will be best. So is there any other questions?
I guess there are no further questions,
Yeah.
so we can stop here. Thank you so much for
Okay.
such an enlightening and wonderful
Oh,
talk,
thanks
Nidhi.
a lot. It was nice. Yeah.
I hope everyone must have enjoyed and answered all the
I
questions
also
very
hope
nicely.
so.
Yeah,
Yeah.
yeah. So I guess we'll see you guys for tomorrow's panel talk. Tomorrow's talk will be by Rishabh Jan. He'll be talking on adaptive optics. Same time, 5 p.m. on this same channel. So I'll be,
So yeah. So I have a question.
yeah,
So can you provide me the YouTube link of the same thing?
yeah, yeah, sure. Then.
Yeah. Please WhatsApp me that. How?
Sure. So yeah, we'd
Okay.
like to end it here. Thank you so much for joining us.
Thanks.